Perfect. Okay, next slide. And just a little bit of background on 3C Ren and the organization helping to put on this training today. So we are 3 counties on the Central Coast working together to improve energy efficiency in our region. So that's San Luis Obispo, Santa Barbara, and Ventura counties here in California. And we offer free programs for both building professionals and households. We are funded by ratepayer dollars, which are collected through the public's good charge, which everyone kind of already pays on their utility bills. And the benefit of being ratepayer funded is that there is no cost to the folks that we get to serve and offer trainings to, like you. And we get to collect some of these dollars from the state and bring them back to our local economy, which historically has missed out on some of these fundings. Traditionally go to the Bay Area or to LA. All right, next slide. And we do offer 3 programs. Our Energy Code Connect program serves all building professionals with AIA and ICC accredited courses. We offer quarterly forums on energy code topics, and we have a energy code coach service where you can ask your energy code questions to one of our expert representatives and get an answer. As well, we offer our building performance training program, which serves both current and new building professionals to offer both technical training, high performance building trainings, and soft skills related trainings for your business. That's the program we're working with today, and we get to do a lot more than just the energy code. We get to dive into a number of building science topics. And then finally, we have our home energy savings program, which incentivizes contractors to help educate consumers and offer measures to consumers on energy efficiency upgrades, and we offer support through rebates. Great, next slide. And if you do see any other staff members on today's training with a background like mine, you see the 3C Ren logo, feel free to message us in the chat directly if you have any questions or comments or would like to learn more. And I'll put a few links in the chat during today's training as well. All right, next slide. Again, my name's Sean Burns. My email is on this slide. You can find it in the slides that we send out with you after the training. So if you have any questions regarding learning units, you can reach out to me. If you did not enter your AIA number during registration, we can help you get those units. We will be offering this, at least the slides for this training afterwards. So we'll share those out with you via email. And we do have some upcoming courses listed here. I'll put a link to our course calendar in the chat so you can check out all of that online. All right. Again, our website is 3c-ren.org, and you can contact that email in the slides, info@3cren.org, or my email, which I'll put in the follow-up email. Awesome. And with that, I would like to hand it over to today's instructor, Judy Rachel, our home performance professional, our home performance expert for duct leakage testing. So Judy, thank you so much for being with us today. Really appreciate it. And the presentation is yours.
Great. Thank you, Sean. Thank you, 3C Ren. So welcome, everyone. Let me briefly introduce myself. I am Judy Rachel. I have been a practitioner of home performance for over 14 years, going on 15 years now. I perform load calculations and design high performance heating, cooling, and ventilation systems for single family residences. I'm not a contractor. I am a third-party independent technical consultant. My area of expertise is in single family residential new and existing homes in dry climates. For 10 years pre-pandemic, I was on the planning committee for the annual Forum on Dry Climate Home Performance, which is an invitation-only conference where we gathered great minds in the field of home performance to spend 3 days learning with each other, with the focus being on dry climates, since dry climates are often a neglected climate in the region in the National Home Performance Conference circuits. I do home performance audits and diagnostic testing of building enclosures and HVAC systems. And I'm part of a team collecting data on single-family HVAC performance for Lawrence Berkeley National Labs and proper refrigerant charge on large commercial buildings for DNVGL. I've been a field mentor for burgeoning home performance contractors and practitioners, as well as being a trainer of building science since 2011. So that's a little bit about me and why I get to be here today in front of all of you to talk about duct leaking basics, testing, and beyond. Today, I want to get into the nitty-gritty of duct leakage testing, the basics and beyond. In essence, we test for duct leaks because we want to quantify how much of the total system airflow is being lost along the way and never delivered to the spaces that we want conditioned. So today we'll talk about the role of the duct system, why duct leakage matters, how the tests actually work, 3 tests that can be performed on a duct system, the 2 most common tests for duct leakage and one that many of you have probably never heard of, how to find duct leaks, how to measure total system airflow as opposed to the delivered airflow, which includes the losses from the duct leaks. The duct system. Duct systems or air distribution systems are the pathways we create in a forced air system for the conditioned air to travel to be delivered into the house. The duct system often travels through unconditioned spaces such as attics, walls, crawl spaces, garages. It's supposed to be a closed loop system, which includes the living space and excludes those unconditioned spaces. When it's a closed loop, it's pressure balanced. The same amount of air that's being brought into the ducts on the way to the air handler is the same amount of air that should be delivered to the house via the supply openings. But when the loop has holes in it, pressure imbalances will occur with potentially unsafe consequences in regards particularly to combustion appliances, as well as energy, efficiency, indoor air quality, and comfort consequences for the occupants. FAU is an acronym for Forced Air Unit, which can also be called the air handler. That includes furnaces, combined hydronic air handlers, heat pumps. Those are all specific types of forced air units. So rather than having to specify the type of appliance, I will be mostly using the term air handler. It's a forced air unit because it contains a blower motor that forces the conditioned air through the air distribution system. The blower pulls air into the air handler cabinet at one end, and that's called the return side, and it blows the air out the other end through the supply duct pathways for the air to get into the rooms of the house to be delivered into the house through those supply fixtures, which are often called registers or grills. Now, I say the blower motor pulls in air on one side. I don't want to give the impression that the return is actually sucking air in like a vacuum sucks in dirt. A properly sized return will be silent because the air is supposed to gently waft back into the return side. It's not a cyclone force sucking of air back to the air handler. Now, the supplies, on the other hand, are supposed to deliver the air at a high velocity. The supply side's job is to throw the air into the room in such a way that the conditioned air entrains the room air, resulting in mixing the room air with the conditioned air, creating a comfortable interior air temperature. Supply side air should be entering the room at a velocity between about 500 to 700 foot per minute, while the return side should be bringing the house air back to the air handler at a velocity of only between 200 to 250 foot per minute. Heat is either removed or added to the air by the evaporator and condensing coils, and now the conditioned air is blown back out through the supplies. The entire system's air tightness is being tested when we do duct leakage. So it's not just the ducts themselves, but the terminations in the rooms, the plenums, the coil box, the air handler cabinet, the condensate line, the entirety of the air distribution system. Part of the duct system, as I said, are the terminations of the ducts that are visible in the house. These terminations often are interchangeably called registers or grills, but those two words really are not interchangeable. One represents a bad design choice, while the other is indicative of a better design choice. A grill is the general term for the louvered cover that's placed over the interior duct opening holes to hide the unsightly hole, but also to create the velocity of the air entering or exiting the grill. Registers, on the other hand, have an integrated damper device. They will have some kind of lever that allows you to adjust the damper blades that are just behind the louvers. Supply registers are what are installed in most homes. But this integrated damper is a great cause of problems in our HVAC systems. They easily allow non-professionals, i.e. homeowners, occupants, guests, they allow them the ability to short circuit the air balance of the conditioning system. Air balancing dampers are a critical component of the air distribution system. To condition a home, the correct amount of air, of conditioned air, needs to be delivered to each room based on the heating and cooling load of each individual room or space. Air balancing dampers give us the ability to adjust the amount of air in each duct so that the correct amount of air is delivered to each room. These dampers are placed within the duct run, not at the face of the grill. And once the system is air balanced, the dampers need to remain in their set position. If any one damper position is changed, the air balance of the entire system is changed. So on the right is an example of a high quality supply grill. It's a single deflection, adjustable curved blade diffuser grill. So to keep my verbiage simple, I'm going to be using the term grill when I talk about the terminations of both supply and return openings. But here's my first caveat to anyone on this webinar who will be doing duct testing or is doing duct testing on systems that they have not themselves installed. You should always presume that registered dampers and adjustable blades on grills have been mindfully set for airflow and throw characteristics by the installer. So respect the installer's work and do not change the position of any movable parts on the grills when sealing them off for testing. Moving on to the significance of duct leakage. System airflow is the amount of air that the air handler is set up to move through the system. The airflow the system is set to is based on the heating and cooling load calculation. The air handler is chosen for its capacity and its ability to achieve the necessary airflow at acceptable energy usage. The air distribution system is designed to effectively deliver the total system airflow to the house and to divvy that airflow up based upon the heating and cooling load of each individual room. The designer is responsible for choosing the equipment and what airflow is to be delivered, as well as all kinds of other things, the sizes of the ducts, the types of grills, the locations of the grills in the rooms. But in terms of airflow, it's a designed part of the HVAC system. The installer, on the other hand, who could also be the designer, is responsible for ensuring the design is followed and that the specified airflow actually reaches the rooms in the specified amounts per supply. The designer would have specified a return large enough to allow that same amount of air to return to the air handler efficiently. Low airflow causes a number of problems. In dry climates like California, Nevada, Arizona, Utah, we need high airflow because we want more sensible temperature relief and very little dehumidification. In humid climates, lower airflow helps with dehumidification, but there is a point at which airflow can be too low, leading to shorter equipment life. So the Goldilocks principle really applies to airflow. We want the right amount based on the load calculation and the climate that the equipment is being installed in. There's three main effects of duct leakage. In a forced air system, air is the medium being used to deliver the heating or cooling capacity. Air leaking from the supply side is a direct loss of that capacity to somewhere else other than the room it was meant for. If the air handler is in the attic, say, and there's a return leak, then in the summer, that hot attic air is being drawn into the air handler. The evaporator coil of an air conditioning system can only change the incoming temperature by about 20 degrees. So if the attic is at a temperature of 140 degrees, then the air conditioning system can only change that to 120 degrees. And in air conditioning, that air of that temperature is not going to be able to cool the air in the house sufficiently. Now, in a few slides from now, I'm going to go over an example of the consequences of return leaks. But I want you to remember how the duct system is supposed to be pressure balanced because it's delivering the same amount of air from the air handler as it's returning to the air handler. So if there's leaks, that balanced pressure concept goes out the window. Now there are pressure imbalances, and those imbalances drive infiltration. An additional odd thing about duct leakage is that it doesn't necessarily equate to less airflow. If the duct system itself is too small to effectively move the total system airflow, then duct leakage can actually increase the delivered airflow. That air will be at the wrong temperature and it will be of questionable quality, but there will be more of it than if you went and sealed that duct system up, causing restrictions to the airflow since that duct system is too small, and you would get less airflow by sealing the system. So we have things going both ways with duct leakage. Dominant supply leaks. When the supply side is leaking, when the supply side has larger leakage than the return side does, this will typically cause the building to become negative with reference to the outside and to any unattached, unconditioned spaces like attics and garages. So if we have a 2-ton system that's designed to move 1,000 CFM, which is 500 CFM per ton, which is a good design airflow for a dry climate. So high airflow is appropriate for a dry climate. So 500 CFM per ton is a very appropriate number. But only 850 of that is making it into the house through the supplies, while 980 is wafting back from the house through the return. The mechanical system is going to make the house go negative. This will drive increased infiltration, pulling in soil gases or backdrafting combustion appliances. In the meantime, those supply leaks could be pressurizing the area they're passing through, such as in this picture, the attic, causing the attic to go positive, creating an even greater pressure differential between the house and the attic. And a pressurized attic or crawl space, if the ducts say we're going through the crawl space and the same situation was happening, that will end up pushing air from those spaces into the conditioned space of the house. And this is going to affect your indoor air quality and your temperatures and your so therefore your comfort in your home. With dominant return leaks, the opposite is true. The house typically becomes positive depending on where the return is in relationship to the house. But the house will typically become positive and the spaces the ducts run through will become negative because the return is pulling more air out of the house, is not pulling as much air out of the house as being supplied into the house. So the house goes positive. Now in humid climates, moist air being drawn into return leaks can overwhelm the dehumidification capacity of the air conditioning system, causing buildings to feel clammy even when the system is operating. Duct leakage also greatly increases the use of electric strip heaters in heat pumps during the heating season. Now in California's hot, dry climate, we rarely need to install heat strips in heat pumps. So if we don't need the additional capacity provided by heat strips, we can help ourselves by not installing them at all. Leaks and return ductwork draw air into the building from crawl spaces, garages, and attics, bringing with it dust, mold spores, insulation fibers, and other contaminants. This is especially a problem when the leaks are downstream of the filter, so that air is bypassing the filter and none of those particulates are getting caught by the filter. If combustion appliances are in an adjacent space that is now under negative pressure, a furnace or water heater in the attic or a California basement, then we still have the issue of possible flame rollout or spillage of carbon monoxide. Positively pressurized conditioned spaces cause exfiltration of your conditioned air. So you're losing your conditioned air through exfiltration with a positively pressurized conditioned space. Let's take a look at how a 15% attic return leak will result in a 50% loss of system capacity. Let's use that 210 system moving 1000 CFM for our example. So 210 system, its nominal capacity would be 24,000 BTU-H. A portion of that will be air temperature change, which is sensible capacity, and a portion of that will be latent capacity, the moisture removal capacity of the system. In a dry climate, we want the sensible capacity to be upwards of 90%. Based on how air moves across the evaporator coil, we can expect at best a 20-degree temperature difference across that coil. So with 75-degree air inside the house entering the evaporator coil, 55-degree air will leave the coil. If there's no duct losses, then 55-degree air will enter the house. This gives us a temperature difference within the house of 20 degrees, 55 to 75. So we've got a temperature difference of 20 degrees. Now the formula to figure out the sensible capacity is airflow in CFM times that temperature difference times the heat carrying capacity of air, which is basically a constant, and we're going to use the constant 1.08. Under these conditions, the sensible delivered capacity of this 210 system is 21,600 BTUs, and that's about 90% delivered capacity. So that's good. One note, I have a picture on the side that is showing what a manometer is reading for a zero duct leakage system. So there can be zero duct leakage systems, and your manometer would actually read low at 25 pascals, which is the pressure difference we use in a duct test, saying that the manometer is not able to read any flow through it. So let's have that 15% return leak. A 15% return leak would mean that out of that 1000 CFM, only 850 are entering the duct system at 75 degrees. That other 150 CFM of air is going to be attic air in this example, since the ducts are running, the return duct is running through the attic. And we're going to say that the attic is at 140 degrees. That gives us a mixed air temperature of approximately 85 degrees, 84.75, so 85 degrees. 85 degrees entering the evaporator coil will leave the coil at hopefully 65 degrees, 20-degree change. This then gives us a 10-degree temperature difference between the air that's being delivered into the house and that thermostat setting of 75 degrees that we want the house air at. So we went from a 20-degree temperature split to a 10-degree temperature split in the house. When we put the 10 degrees into our formula of our constant, the heat carrying capacity of air, times our temperature difference, times the CFM for the system, we come out with 10,800 BTUs. which is a 50% loss of capacity. Now, 15% is a significant number in California because that's the amount of duct leakage that is allowed when new equipment is attached to an existing duct system. So building code is essentially allowing contractors to install brand new equipment and attach that to a duct system that is not capable of delivering anywhere close to the system's capacity into the house. Duct leakage has a significant effect on system performance. Right, the principles behind the testing itself. The purpose of duct testing: to estimate the HVAC capacity losses due to air leaks, to diagnose where duct leakage locations are, to measure the effectiveness of the air sealing efforts. And then there's for code compliance, documenting and certifying the leakage for code. There are two main companies that manufacture duct testing equipment, RetroTech and the Energy Conservatory. The new RetroTech duct tester is what they call their piece of equipment, has a place mounted on the side of the blower fan for their digital manometer. So I don't know if you can see my cursor, but I'm circling where their manometer is mounted on the side of their fan. TEC's equipment, the Energy Conservatory, TEC, their manometer is either attached to their mounting board, you can hold it in your hand, place it on the floor near the equipment. There isn't a place to mount it on the fan. And so these are both calibrated airflow measurement systems to test for the tightness of forced air systems. The brains of the calibrated equipment is the manometer. We use the same manometer for most of our pressure testing. These manometers can be used for standalone pressure measurements or as the brains for various pieces of equipment, such as the duct testing equipment, blower doors, pressure pans, exhaust fan flow meter boxes. We need to attach the brain to the piece of equipment that we're using. All of the newer manometers are dual channel, meaning basically that they are two manometers in one instrument. The DG gauges, the DG700 and the DG1000, are manufactured by the Energy Conservatory, and the DM gauges, the DM2 and the DM32, are manufactured by RetroTech. I will mostly use the DG700 for pictures and to explain gauge setup because it just has a great visual display to show and explain what's going on with the manometer. You can see the two channels. There's the A side and there's the B side. Channel A will always read out pressure. Channel B is measuring pressure, but we can program it so that it converts that pressure to airflow or velocity. It gives us a number of different metrics that we can change the B side to give us readings that we don't have to go to charts to convert the pressure to what we want, say cubic feet per minute of air movement or foot per minute for velocity. Both sides have input taps and both sides have reference taps. They're differential pressure gauges. So the pressure reading is always in reference to a secondary location, such as the house with reference to outside or the duct system with reference to the house. All of the other gauges besides the DG700 are not as clear at first glance, especially the input and reference taps. RetroTech systems are set up so that you follow their color coding system, hooking up colored hoses to the matching color pressure tap. This is kind of their attempt to make setup idiot-proof. They do label the pressure taps, it's just not as clear. And it's often in very small print that is not contrasting very highly from the background color. So I think that it's important to know how the equipment actually works, and therefore you can figure out where the hoses should be attached to, if the hoses are attached right or not, what tap they should be attached to, and what exactly attaching them to that tap is doing. This allows for quicker troubleshooting, and in case you don't have a particular colored hose, you can still set the test up correctly using any color hose. So I've given you reference of the taps for the different pieces of equipment. This is the newer RetroTech gauge that's Bluetooth enabled. And this is the new TEC gauge that is Bluetooth enabled. The Energy Conservatory had a bit more faith in the intelligence of the individuals using their equipment. So although they've actually started to provide a colored hose, they provide us with colored hoses, and they've adopted actually a hose setup assist function in this new DG1000 gauge. They've not gone so far as to give us color-coded taps. The different colored hoses from Energy Conservatory actually tell us about the length of the hose, and dealing with all of these hoses can be quite the bird's nest mess. And so knowing that I don't have as far to reach with a particular hose can help me decide which hose I want to grab for, for that part of the setup. So the red hose is the shortest hose. It comes at 10 foot, and the green hose is 15 foot long, and the clear hoses come in 30-foot lengths. Now, of course, you can cut your hoses to whatever lengths you want them to be, but that's what you'll get from Energy Conservatory when you get the different colored hoses. And it absolutely does not matter what color hose you choose to use. They are all the same with the same diameter. What is important is that you put the hoses in the correct place and attach them to the correct tap for the test that you're doing. Testing for duct leakage is based on the fact that if there is a hole and there's a pressure difference across that hole, there will be air movement through that hole. So there's three variables: the hole, a pressure difference, and flow. Knowing any of the two variables means that you can calculate the third variable. And particularly when we know the size of the hole and we know the pressure difference across that hole, we can calculate the quantity of air moving through the hole. The duct testing equipment provides us with holes of a known size. It provides us with the ability to create a uniform pressure across that hole via the fan. The manometer does the math and converts that information to airflow, which in this case is duct leakage. By sealing up the duct system at the grills, attaching the test equipment to the duct system at a return, choosing a hole size, turning the fan up to the test pressure, which is typically 25 pascals, the manometer will calculate the leakage of the air distribution system. These are the holes of a known size for the Energy Conservatory equipment. The fan itself with no rings on it is called open ring. The equipment comes standard with 3 additional rings, ring 1, 2, and 3, they're labeled. And then there's this chart showing the fan flows, the calibrated fan flows for each ring size. And you may notice that the ring flow rates overlap. So for best test results, you want to take your reading with the smallest ring that is calibrated to the airflow result you're getting on the manometer. So as an example, if you have ring 1 installed and you've brought the fan pressure up to 25 pascals and you're getting a reading of 300 CFM or less, you should repeat the test with ring 2 installed for a more accurate result. Now ring 4, there's ring 4, is an optional ring. And so it's for purchase additionally. And it's for really tight duct systems. It's for duct systems that leak 25 CFM down to 2.4 CFM. And the story of ring 4 is kind of fun, I think. There was a group of home performance practitioners here in California who were doing tight duct systems. Their goal was to have zero leakage duct systems, and they taught themselves and their crews to make really tight duct systems. And so that picture I showed you earlier was from one of our systems that we built that we couldn't get a reading on ring 3, which basically is telling us that the flow rate through the duct system was 9 CFM or less. So potentially it is a zero leakage system. Well, they became friendly with Gary Nelson, the founder and owner of Energy Conservatory, and were telling him that they thought they were building zero leakage duct systems, and that they were very curious if they, really were, and what if they were working on passive houses where you definitely, need to have very tight duct systems, which was not what they were working on. They were just doing home performance on, standard houses, and they basically kind of badgered Gary into him deciding to develop an even smaller ring size. And so he developed it, and he was one of the invitees to the Forum on Dry Climate Home Performance that I mentioned, that I'm a part of the planning committee. And one year he came to the forum with the ring 4s, and he signed them, a bunch of them, and gave them to the contractors that come to the conference, who we know consistently do tight duct systems. So it is something that's for sale from the Energy Conservatory now for tight duct systems, and that's why the ring 4 came into existence. This is Retrotech's rings and what they look like. They call them range plugs. They don't make their flow rates for their rings easily available. So it makes it a bit more difficult to know if you're testing with the best ring for test accuracy. Their website states that there's a proprietary software that you can download, which would give you that information. I own Energy Conservatory equipment, so I didn't choose to download that software from Retrotech. The numbers that their rings are named actually refer to the approximate hole diameter in millimeters of their rings. 25 pascals is the test pressure that is most often used for residential duct leakage testing. This is the choice that's been made across the industry, so it's this industry standard. It's actually impossible to test for duct leakage under actual operating conditions. So we use this 25 pascals as a proxy. Now, there are some test standards out there that have testing done at different test pressures than 25 pascals. So if you are testing to one of those standards, then use the test pressure appropriate to that standard. Under actual operating conditions, the pressures throughout a duct system vary, with the highest pressure being closest to the blower motor and the lowest pressures are out by the grills. This is important when prioritizing duct sealing efforts. Leaks at and close to the air handler are under the highest pressures, so even if they might not be of the greatest size, more air will move through those leaks because they're under a higher pressure difference across those holes. Now, in terms of loading order, we definitely want to repair catastrophic leaks like disconnects. And then we're always concerned about return leakage that may cause problems with combustion appliances or bring carbon monoxide into the duct system through the return. Then we have the leaks under highest pressure. And from there, you start moving out from the air handler. So those close to the air handler, then further out away from the air handler. As those leaks are under less and less pressure, the further from the air handler we get. These are the two main duct leakage tests that people are taught. There's total duct leakage, which measures leakage from the entire air distribution system and leaks to both the unconditioned and conditioned spaces. So it's leaks through the evaporator coil, the condensate line, the air handler, the plenums, any mixing boxes, connections, ducts, boots, through the unconditioned and conditioned space. Then there's duct leakage to the outside. And it is measuring only the air leakage outside of the conditioned spaces. And so what we're doing with that test is we're neutralizing any duct leakage into the conditioned space by bringing the house to the same test pressure as the ducts are being put under. And since there's no pressure across those holes now, there will be no air movement. And so that's how we get rid of the leaks to the conditioned space and are able to only quantify the leaks to the unconditioned space. Okay, so that's basically how duct testing works. Now let's take a very close look at the total duct leakage test. Setting up the house. We will adjust all the mechanical equipment, including the air handler fan, so that they will not turn on during the test. So the thermostat gets turned to off. The water heater gets turned to pilot. Bathroom exhaust fans, laundry exhaust fans, kitchen exhaust fans are all turned off. Attic exhaust fans can depressurize that attic space, which is our unconditioned space. And if that space gets depressurized while we're doing our test, we don't have a 25 Pascal pressure difference across the duct system, which would create inaccuracies in our test result. So we need to make sure that attic exhaust fans don't come on while we're doing our test. Clothes dryers suck air out of the house. So clothes dryers need to be off. So all mechanical equipment needs to be off. And combustion appliances should not fire, just in case there is a pressure difference created in the house due to leaks in the ducts. Filters are removed from the duct system. We're not trying to measure the airflow or pressure drops or anything across filters. We want to be able to get the air through the entire duct system, so remove filters. The supplies and return grills are all temporarily sealed off, except for the place that you're going to decide to attach your duct testing equipment. That gets sealed off with the duct test equipment. It gets sealed off around the duct test equipment. There's all kinds of ways to seal off the supplies and returns. The important thing is that you create a good seal that won't get blown off while you're doing the test. And so I cut pieces of a flexible but sturdy plastic that to different sizes that are kind of typical supply grill sizes, and then I will often kind of patchwork them together if there's a return that I need to tape up as well. So this picture is of me taping up a second return in a house with my patchwork of extra plastic pieces. And that way I end up wasting less tape because I reuse those plastic pieces over and over. I have been reusing them through my entire career, have not had to replace them. If there's multiple returns, so up to 3 returns, the best place to attach the duct test equipment is to the largest and closest return to the air handler. And if there's more than 3 returns, then you want to attach the equipment to the air handler blower compartment itself. The most difficult place to seal is if there's any ventilation air inlets, which are directly connected to the duct system. You need to figure out, can you seal those off outside the house, which unfortunately often those are through the roof. So that can present difficulties. Easier if they're going through a wall to seal off that way from the exterior of the house. Otherwise, you do need to figure out how you can disconnect them, seal them. You got to figure it out, or else you're not going to be able to test the system, because that will show up as a huge duct leak because your equipment can't figure out that that's an intentional penetration in any way to take that air out of the duct test. So you've got to figure out how to seal that up. This picture is an improper sealing of a supply grill, or of any of the grills. When sealing off the duct system, the seal needs to extend to the interior finish. So unlike what's shown in this photo, you do not wrap the tape or whatever you're using actually around the grill edges. And this is the reason. Boots are often not sealed to the interior finish. So let's take a look at what we're seeing in this picture. If you can see, here's the drywall and here's the boot. So there is this huge gap on this side. And since the boot actually isn't sealed at all, even though the gap is much smaller at other places, those are still effectively air leaks that if we don't seal to the interior finish, we would be missing in our duct test. As the supply air hits the back of the grill, some of that air will decide that the path of least resistance is to turn and go through that opening between the boot and the interior finish, rather than, say, fighting the rest of the air that's squeezing through the grills, where the velocity is increasing as that air has to squeeze down and squeeze through the grills. So we have to make sure that we tape to the interior finishes so that air is not just leaking out past our seals and we're not catching it in the test. Caveat number 2, be careful when sealing using tape products to interior finishes. Many paint jobs are not done well, and when you do the test and you've taped to the interior finish and you go to peel the tape that you've applied to the wall or ceiling, the paint will often come off with the tape. And this happens even when using painter's tape. So you have to be careful with just how much you pressure push the tape to the interior finish, and you just got to be really careful. Another aside, in talking about balancing dampers, there is a balancing damper stuck back in the duct of this duct run. So this duct could be air balanced. The grill would be removed and you'd reach in and you would open or close the damper a bit until you were able to measure that you were getting the right amount of air out of this duct. So balancing dampers need to go in the duct system, and they go into different places in the ducts themselves, depending on whether you've got a home run system or a trunk and branch system, or whether there's accessibility to where the ducts are running, but they don't go at the face of a register. That's the wrong place to put your balancing dampers. So we've still got more setup to do. The test is supposed to be performed at 25 pascals across the duct system. So remember, we talked about the pressure changes that can occur based on whether there are dominant supply leaks or dominant return leaks. If the unconditioned space becomes pressurized or depressurized when the test, then the test is not giving you a test result at that induced pressure of 25 pascals. the test result is at some other unknown pressure resulting from that pressure change in the unconditioned space. If that space is pressurized to 5 pascals, then you've only got a 20 pascal pressure difference across the duct system, even though your manometer is showing you 25 pascals in the house. One of the best ways to make sure that the unconditioned space is not undergoing a pressure change is to open the space to the outside, which might mean opening any access vents or access panels or doors, anything there is that is potentially closing that space off from the outside. And it might mean actually opening, say, the attic access hatch to the house, which we've opened the house to the outside because we're always going to have a door or window open, at least a crack between the house and the outside for the total duct leakage test. If the duct test fan is going to be installed in an unconditioned space, say connected to an air handler located in a garage or a crawl space, California basement, then you need to open vents, access panels, or doors between those spaces and the outside. And you need to run your tube from the A side reference tap into the house to measure the duct pressure with reference to the house. There are a couple of acceptable places to attach the test equipment up to the duct system. If you're using the flex duct to connect to the return, you'll want to minimize any bends by extending the flex duct with the fan in the straightest line possible away from the return. So you would never be testing this close to a low sidewall return. This picture was shot for marketing purposes, not for correct setup purposes. What is correct about this setup is that the transition piece flange from the flex duct attached to the return is centered over the return. And you do want to center the duct test equipment over the return. You don't need to use the flex duct. It's not a necessary part of the test. It's just to help you when the return you're hooking up to is in a difficult position, in particular, like an attic return. We couldn't attach just the fan to a ceiling return. So you can just install it directly to the return grill and or to the blower compartment of the air handler. So attaching it to the blower compartment of the air handler, typically we use cardboard cut to the size of the opening of the blower compartment. You can use the flex duct or not. If there's any kind of obstruction, or if the blower fan is kind of right there at the opening, it's big and it's right there at the opening, so that in and of itself is making an obstruction to the duct fan and its air flow and movement, then you want to build the duct, you want to build out so that you're giving more room for the flow that's going through the duct fan to be able to spread out and go up into the system. So you might build out by using a cardboard box cut down a bit. So I found that construction and diagnostic testing is basically kind of an arts and crafts project on a grand scale, and you figure out what materials you have and you cut and paste them and tape them until you've got the setup that works. So we're done with our paper mache project and have managed to attach the test equipment to the duct system. Now we choose what size hole to test with. And this isn't a big deal. You just choose to test open ring or to install a ring, and you just make the choice. The manometer will give you clues as to whether you've made the right choice or not once you start turning the fan up. And if you haven't made the right choice, you just stop the test, change the rings on the test equipment, tell the manometer that you're putting on a different ring and what ring that is, and just restart the test. The RetroTech range plugs kind of pop on and off their equipment energy conservatory rings have a nozzle, which you can kind of see right here in the picture. And that nozzle needs to be placed pointing inward toward the fan motor. I have seen people test with it. Turned out that's not correct. They also supply you with these connecting trim pieces that hold the ring in place. So you can just pop those on to hold the ring in place. And you only put one ring on at a time. You don't nest multiple rings. So if you're changing rings, you literally change the ring. You don't just nest one ring into another with the energy conservatory equipment. Okay, so we're getting there. Now we need to attach the hoses and program the manometer. No matter whose equipment or whose manometer, the A side is always set up to test the duct system with reference to the house, which is really, the house at this point is really connected to the outside. So I think of A as standing for air, and the air side is the duct system. So that tells me that I take my hose and I attach it to the input on the A side, and the other side needs to get into the duct system somewhere. So as illustrated here, one of the places you can measure the duct system pressure from is through a supply. So you put a small hole in the seal that you've made over one of the supply grills and stick the end of the hose through that hole past the grill louvers and slightly up into the boot, and then tape that hole around the hose so that it's closed, and tape the hose so that it will actually stay in place. The B side is measuring the fan pressure. So B stands for blaster for the energy conservatory equipment. It's a duct blaster. So B stands for blaster. So I know that I'm hooking up my other hose to the input side on the B side, and the other end of that hose is going to go to the tap that is on the blaster fan itself. And what you're measuring on the B side is the duct blaster fan flow with reference to where the flow sensor is. And the flow sensor on both energy conservatory equipment and RetroTech equipment is on the inlet side. So if I'm pressurizing the duct system, I leave the pressure tap open to the house, since that is where the flow sensor is facing and getting its reading from. Here's a picture of RetroTech's setup for the test. It's basically the same. The hoses are color coded to the tap, so you can identify the colored tap, attach a matching hose, one end to the tap, the other end into the duct system. The fan side has this, they call it an umbilical cord with a bundle of hoses coming out of it. The yellow hose attaches to the yellow tap on the fan and to the yellow tap on the manometer. If you have one of their newer fans, there will be a green tube in the umbilical cord bundle, and this tube will attach to the green tap on the manometer and to the green tap on the fan. And this is how RetroTech has you reference their flow sensor. They call these fans self-referencing. And the advantage to this is that if you choose to depressurize the duct system rather than pressurize the duct system, all you have to do is turn the fan around and attach the fan inlet side into the flex duct, and you don't need to change hoses or anything. Okay, we still have to program the manometer. Once again, I'm going to use the DG700 because of how visual it is. Step one, you want to choose your mode. And the mode for duct testing is either going to be pressure flow or pressure flow at 25. Either one is fine. They both work for duct testing. Step two, you're going to choose the correct device. And so RetroTech has their whole list of devices that you need to scroll through and choose. With the Energy Conservatory, there are 2 duct blasters that this manometer can be used with. One is the DBB, and the way to know if you have a DBB is if your manometer has a black case. Like all the pictures I've shown so far of energy conservatory equipment, they have all had the black fan case, so those are all DBB. The older energy conservatory fan had a white fan case, and that is the DBA. There's not a lot of those out there anymore. Those were their original duct blasters. Depending upon the age of the Retrotech fan, you will probably have the 340X duct tester, or it may be the 200. Units are the next thing that you should take a look at. Depending on your manometer, it may default to CFM when it's turned on. The Bluetooth enabled manometers, I think from both companies, may default to the last units you were using. So you may have to change units, you may not. So you just need to take a look and figure out if you need to change the units back to CFM or not. And then there's the config, and that the config is the ring size. And so once again, you just need to make your best guess as to what ring you want to start testing with and program that into the manometer so it knows what flow range it can accurately measure at. And if you've chosen the wrong ring size, you just stop the test, change rings, make sure to change the ring both physically on the device and on the manometer. It's the most common mistake is to forget to change the configuration on the manometer when you've changed rings, and then you don't have a correct test result, and you have to go through some graphs and some mathematics that Energy Conservatory has a number of tables in their manual, plus you can call them for support, and I'm sure you can probably call Retrotech for support as well, but it's not a lot of fun to look at your picture of your test at the end of the day and realize that you had a different ring on the fan itself than what the manometer was programmed for. All right, so what's the difference between pressure flow at 25 mode and pressure flow? Well, there is some advantage to testing in pressure flow at 25. The pressure flow mode is the flow reading on channel B at any given moment is based on the real-time pressure reading on channel A. So if my manometer were actually in pressure flow mode in this picture I have here, then the B channel would actually be reading 56 CFM instead of 57 CFM, because the real-time flow through the fan at a test pressure of 24.4 CFM and the pressure on the B side through the fan flow sensor is not 57 CFM, it's actually 56 CFM. So it's the real-time reading. Pressure flow at 25, which is what the manometer is set at in this picture that I took, is still measuring the duct pressure. So channel A is still measuring the duct pressure, while channel B, the display on channel B, is giving you an estimated total duct leakage number as if channel A were at 25 pascals. The leakage estimate on channel B is determined mathematically by adjusting the measured airflow from the fan using the real-time channel A duct system pressure reading and using a correction factor, which is called the can't reach pressure factor. So at 24 pascals, that can't reach pressure factor is 1.02. It's very, very close to what the actual reading would be at 25. So if my manometer were in pressure flow, the B side would be displaying 56. With the manometer set to pressure flow at 25, the manometer is multiplying 56 by that can't reach pressure factor of 1.02, and it's displaying 57 as a result at 25 pascals. So let's say you're turning the fan speed up, trying to get to 25 pascals of pressure difference. So the main time that we really need that can't reach pressure factor is if we're having a really, really leaky duct system. And say you could only get the test pressure up to 14 pascals on the A side. That's the pressure between the duct system and the house. On the B side, the pressure of the air being pulled across the fan flow sensor is being measured. And then that pressure is mathematically translated to CFM. And then for our example purposes, let's say that the B side was reading 1200 CFM. The correction factor for a duct pressure at 14 pascals is 1.42. So if you're in the pressure flow at 25 mode, that 1200 CFM of fan flow on the B side would be multiplied internally in the manometer by that can't reach pressure factor of 1.42. So the CFM displayed on the B side would be actually 1704 CFM at 25. When using this mode, the pressure flow at 25, the closer that you actually get to 25 pascals, the less of an error there is in that correction factor. So you don't have to be so careful as to get your fan exactly to 25 pascals. If you get within plus or minus 5 pascals, so if you get to 20 pascals of pressure up to 30 pascals of pressure, you can stop the test and take your reading at 25. And you'll have an accurate reading. The other thing is that pretty much as soon as you turn the fan up, if you're in pressure mode at 25, as soon as the B side starts displaying numbers, you're going to have a sense of what the final number is going to be because that correction factor is being applied. So that flow that you're seeing is at 25. And so right there, I can take a glance at the table of flow ranges and see if I have the best ring installed for the test. And if I don't, I just turn the fan off, change rings, change configuration in the manometer, and turn the fan back up. And once again, I'll see the reading. And now hopefully I'm, have the best ring on for my final reading. And then if I can get the system all the way up to that 25 or plus or minus 5, then I have a good accurate test. The Energy Conservatory in their manual provides a table of all the correction factors from 5 pascals up to 24 pascals. So if you were in pressure flow mode and somehow didn't realize it, or for whatever reason you needed to use the correction factor from what you got and you were in the pressure flow mode, you could just look at the correction factor and multiply that to your B side reading, and you would get your pressure flow at 25. Now we need to decide whether we actually need to adjust for a base pressure before we actually start the test. So during mild weather conditions, little wind, less than 20-degree temperature difference between the inside and the outside of the building, the baseline duct pressure will typically be less than 1 pascal, but we need to check because that's what testing and not guessing is all about. If it's a very windy day, or there is a large temperature difference between inside and outside, and the ducts are located in conditioned zones, in unconditioned zones, the attic, crawl spaces, garages, then there probably will be a pressure differential between the duct system and the house that's greater than 1 pascal. And if that's the case, the first thing we need to do is adjust for that pressure difference. To do that, and to check to see if there is a pressure differential, you need to close the fan off. So there is a nylon cap that Energy Conservatory provides, or you use a piece of tape over the hole for the RetroTech fan, and you take a look. And if it looks like that base pressure is bouncing at 1 pascal or more, then we should adjust for base pressure. And what that just entails is going into the baseline mode, and on the DG700, you just push baseline, then you push start, you watch the A side, and when the pressure reading on the A side stabilizes, you press enter. And now you've got the baseline adjusted into your manometer and you can start your tests. So this is what the pressure tap and the electrical receptacle looks like on the duct blaster fan. It's similar, they're similar on Retrotech. And this is the speed controller on the mounting board for the fan speed. Newer manometers are all set up for cruise control, and it just takes an extra little cord to be set up to actually be able to set up cruise control and not have to manually control the fan. Retrotech has always had you choose a percentage of fan speed, or if you're they've always kind of had a type of cruise control going on, or you can manually control their fans with a control knob that is on the fan itself. So to start the test, once the house and equipment are set up and you decided whether you needed to adjust for any base pressure or not, you remove the covering so that the fan is now open. You turn on the fan, and either using your cruise control or the manual controller, you're going to bring the duct system up to 25 pascals, plus or minus 5 of that if you're in pressure flow at 25. And at that point, decide if you have the correct ring installed. If you do, great. If not, stop the test, change the ring on the manometer, and restart the test. Note what the airflow is displayed on the B side, and take a walk around your job site to make sure that your tape job is holding up, that none of your tape has blown off and you're getting leakage through what should be sealed. So fix any tape that has come undone, any of your seals that aren't on well. Go back to your manometer, make sure that you're at that pressure difference of 25. And then you can hit the hold button, take a picture of it. You can turn the fan off once you hit the hold button, and you will still see your reading and record your duct test reading. If by some chance you get a series of dashed lines on channel B, when you are in, so with Retrotech, if you get those dashed lines, what you need to do is install a flow ring. So if you were in open ring, you need to install a ring. And if you had a ring on, you need to install a smaller flow ring. With TEC, when the dashes are continuously displayed, that's going to happen potentially in the at mode, the at 25 mode. The pressure is below 5 pascals, and so you actually need to install a larger flow ring or potentially remove the flow rings and test an open ring. So those dashes are telling you different things for the two pieces of equipment. Low is sometimes displayed on the energy conservatory manometers. When low is displayed either continuously or fluctuating with a flow reading, the pressure signal from the device is too low to provide a reliable flow reading. Now, this can happen as you're bringing up your test pressure when you are in the at 25 mode. And so what that's saying is that basically the correction factor at that point is making the manometer think that you're not within the range of the ring that you're on. So you do need to get closer to your test pressure to see if it stops flashing between low and a flow before you decide to change rings or not. And so if possible, you're going to install a flow ring if you were testing an open ring, or install a smaller flow ring if you're getting low on your manometer. And that's what we get when we test a very tight duct system and we can't get a reading. So it's kind of the ideal thing that we want to get when we're testing on the smallest ring, and we can't get a reading. that's telling us that we potentially have an airtight duct system, or definitely one that is leaking. If you're using, so in this example, in this picture, we were on ring 3. And so if you have that smallest ring on, then that means that your duct leakage is less than 10 CFM if you get this reading. To pressurize or to depressurize, it doesn't really matter. The test results will be similar. Depressurization has the one advantage that the negative pressure will be pulling the seals on the grills to ensure a tighter seal. Pressurization is pushing against those seals and could potentially pop some of the seals if you haven't done a good job sealing off the grills to the interior finishes. The tester needs to take a look at the manometer and do a quick check of their sealing job to make sure that, that no seals are leaking. It's definitely easier to pressurize with energy conservatory equipment. It's not that big of a deal, but you do need to install what's called a flow conditioner into the flex duct, which is why you have to use flex duct if you are depressurizing with the energy conservatory equipment, because that's where that flow conditioner gets installed, is in the flex duct. And then there is an additional hose that you have to attach from the reference port to the duct testing fan, whereas the Retrotech equipment, you've already attached 2 hoses to your fan for any of the testing if you've got their newer fan. And you can't use the open ring configuration when depressurizing with energy conservatory equipment. So when conducting the depressurization test, the effects flexible extension duct must always be used to connect the duct blaster. In addition, the flex duct has to be connected to the system at the central return or the air handler cabinet, and it needs to be stretched relatively straight and tight and definitely for about 4 feet in front of the duct blaster fan itself, so that the airflow going through the flow conditioner is actually, it's kind of getting straightened out, and then that flow conditioner is straightening out the turbulence and getting rid of the turbulence further. So if you have that newer Retrotech self-referencing fan, there already is that green hose attached. And the only difference is that you can just flip the fan around over the top of the range rings. And for either test, if you do need to change rings, you need to take the fan off of the flex duct, change your ring, and then reattach to the flex duct. This is what basically is happening. That's a picture of the flow conditioner on the right, and then energy conservatory, you're just putting the flex duct over the fan inlet and not making any other changes. All right, duct testing best practices. Location, where do we measure the duct system pressure? So I've been showing you putting the tube into the supply, and putting it into the supply closest to the air handler is kind of a good practice. You don't need to use a static pressure probe if you're putting the hose into a supply. And essentially, if a duct system leaks less than 100 CFM, then the test point location is not going to affect the results in any significant way. You can also test in the supply plenum. So you drill a hole in the supply plenum, you do need to use a static pressure probe, and that static pressure probe does need to point into the airstream, so towards the return. Another place that you can put the static pressure probe is if it's a trunk and branch system in the main supply trunk, pointed towards the airflow again, so towards the return. And then if you're testing a zone system, you need to make sure that all the dampers are open throughout all the zones. Otherwise, you're going to have to repeat the test and test each zone separately. When considering where to install the equipment, it's important to think about airflow restrictions. And so, as I said, if there's up to 3 returns, then the largest return, which is hopefully the one closest to the air handler, is where to install the equipment. If there's 4 or more returns, attach the equipment to the blower compartment of the air handler, and then install the transition piece or the fan in the middle of the grill. But I have found that often the return duct is not actually coming into the center of a grill. So you do need to look through the grill and see where exactly the duct is truly coming in from. And that's where you want your equipment attached, is over where the air is truly coming into that boot. Airflow restrictions cause back pressure against the fan, and that causes inaccurate test results. So RetroTech doesn't give us any guidance as to what the limitations of their fans are. Energy Conservatory publishes that their fans can handle up to 100 pascals of back pressure, but as the back pressure increases, the total airflow of the fan that the fan can measure decreases. So not by a ton, but it does decrease. And that's something that you should be aware of. If you think that where you're hooking your equipment up to is going to be restrictive, you can check to see. You just need your manometer, so another manometer or the one you're using. You just need to hook a hose up right at the spot where the equipment is attached to the return, is where you're going to measure for back pressure, and to determine whether you're going to be able to get an accurate reading there or not. So one thing I do want to point out in this picture as well is, now we've gone over the hose setup already, and what you'll notice is that there's an additional hose put on the reference A side and running someplace. And so what might the reason for that be? Well, this could be a tight hallway, a short hallway. There could be, a great big piece of furniture that is not too far away from the inlet of the duct blaster fan. So the fan could be creating a lot of turbulence in the hallway, and this reference tap would be picking up that turbulence being this close to the fan. So one of the ways that we can smooth out that and that turbulence, not get it picked up by the fan to have it affect our readings, is to attach a hose to the reference tap, and then run that hose to some other room of the house where there's not going to be the effect of that fan. The other reason that hose could be there is that potentially they could be setting up for duct leakage to the outside testing. And one of the ways to set up for duct leakage to the outside is to run a hose from your manometer to the outside. So we're going to be looking at that shortly. When attaching the squared around transition piece to cardboard, which definitely when you're attaching to the air handler cabinet, we need to pretty much always attach to cardboard. Also, it's great to cut a bunch of pieces of cardboard to kind of standard return sizes, and just have a number of pieces of cardboard with a hole already cut. But in cutting that hole, what you need to do is not cut the round. What you need to do is actually trace the outside square and cut 1 inch in a square. And that's how you make a proper hole in your pieces of cardboard, so there isn't any kind of air restrictions when you attach the duct blaster fan. For greatest flow measurement accuracy, I've said we want the smallest ring opening while still providing the necessary pressure. And another important point is to always stand at least 12 inches from the side of the fan inlet. You never stand in front of the fan, and you don't want anything blocking the fan and being in the front of the fan. That will affect the flow reading. There's times when we're just not going to perform a duct test. If the duct is wrapped in a material containing asbestos or suspected to contain asbestos, you do not pressurize or depressurize the duct system. You forgo duct testing. Sometimes you just kind of got to use your good sense and make choices. This system was actually a completely unducted return, and the return was over the crawl space. So it wasn't even a system that you'd want to turn on in somebody's home. It's severely compromising the indoor air quality of the house. It's got an old hammock filter system. There's plenty of room for the air to decide to just go past that filter, and there's no filter that is good enough to clean unadulterated crawl space air. So in this case, you really could just go to telling the homeowner they really shouldn't be turning the system on and they really need a new system. Sometimes you need to make those choices. All right, let's move on to the half Nelson test. So knowing whether there is more supply or return leaks can help direct duct sealing efforts. And the half Nelson test is a fast method which estimates the ratio between the total supply leakage and the total return leakage area. And those supply and return leaks, they have different energy impacts. The ratio relationship is based on size, and it's not quantitative. So those numbers are not telling you airflow. They're just quantitatively telling you, they're not quantitatively, they are relatively telling you a ratio relationship. So in my two pictures, I have a big return leak and supply leaks that are half the size. So we've got basically a 2-to-1 ratio of return leak to supply leak in the picture. And both pictures are that same relationship. So you could have a smaller return leak, and on the supply side, those small leaks could be half as much as well. So it's not actually telling you the size of the holes, it's telling you the relative relationship of the holes, which is telling you whether there's more supply or return leakage in a system. The test is named for Gary Nelson, who I talked about before, the founder of the Energy Conservatory. He came up with the test. And what you do with this test is that it's performed after you've done your total duct leakage and or total duct leakage to the outside. All the grills are still sealed off and the equipment is still set up. You need to set the manometer to pressure. So not pressure flow at 25. It has to be in pressure. Both sides of the manometer will be measuring and displaying pressure. You're going to close off the duct tester fan opening. So you're closing off the entire system. Now the rest of the test has to be done very quickly. You're going to turn on the thermostat, either in fan only or air conditioning, very, very quickly, because you're starving the system of air. The manometer is going to register numbers on the A and B side simultaneously. You hit the hold button on the manometer, so you've grabbed those readings. Then you quickly open the fan up. So pull that fan cap off or pull the tape off, and then quickly turn off the thermostat. The test is done. This reading shows that the majority of leakage is on the supply side. The side showing the smaller number is the side where there is more leakage. That side of the system was not able to hold as much pressure. There's more leaks, so more air was able to get out. The supply side is always your A side. That's the duct system is always being tested on the supply side, so it's positive. And the left side, the B side, is always, I'm sorry, so my left and right is not good. But the B channel is always going to be negative, because that's where the duct equipment is set up to. It's set up to the return side, and the return side is negative. So you can ignore the negative or positive, but look for the smaller number, and that is your leakier side. And that's you. And you can't just do simple math and say that, oh, this is the ratio relationship of the two sides. And it's not important that you actually know what the actual ratio relationship is. It's just a quick way to find out whether you have dominant supply or return leaks. Right, duct leakage to the outside. The house and equipment setup. So your duct test equipment should already be set up. Your system is all sealed off. You're either pressurizing or depressurizing. You've either pressurized or depressurized the duct system. And you can leave that all set up the way it is. The one thing that you do have to do is to change your manometer to pressure flow. It has to be in pressure flow for duct leakage to the outside. That door or window that you had open for total duct leakage test needs to be closed. We're closing the house off. If you've opened any of the unconditioned spaces up to the house, those need to be closed off. And you need to set a blower door up in the house, and you're going to set it up to pressurize or depressurize the house based on whether you pressurized or depressurized the duct system. The procedures. You're going to begin with the duct test equipment off. You're going to bring the house to 25 pascals with the blower door. And we're only concerned about the pressure of the house with reference to the blower door. We're not interested in the B side of the blower door manometer, just the pressure. So then you're going to pressurize or depressurize the duct system, which is neutralizing that test pressure across the ducts in the conditioned space. So if you did not add that additional hose to your manometer setup, so your hose is still set up as in this picture with the duct system with reference to the house, you're going to notice when you go over to the duct test equipment that your pressure on the manometer is actually reading a bit negative if you're pressurizing the house. And when you turn the duct blaster, the duct fan on, you're going to take it from that negative to 0. And that's going to neutralize the duct pressure across the conditioned ducts and the house. If you ran a tube from the reference tap on the A side to the outside, then you're going to notice that so in that case, you're going to take the fan all the way up to 25 pascals. So once you have done that, know whether you're taking it to 0 or whether you're taking the duct pressure to 25 pascals, then you're going to confirm that the blower door is actually still at 25 pascals. It typically will have changed some. And this is where cruise control really comes in handy, is hooking up that cruise control and letting the cruise control continue to adjust the house back to that 25 pascals as you're turning the duct pressure fan to where it needs to be. So once you've confirmed that the house is 25, you need to then go back to your duct equipment and bring that to 0 or 25. And you really actually have to go back and forth a couple times to make sure that you've got them both where they need to be, because right now we don't have an app function happening. We don't have a correction factor happening. We need to get to those numbers, 25 pascals across the duct system and to the 0 or 25 pascals on the duct test equipment. And once those numbers stabilize, then you take your flow reading off the B channel of the duct test equipment, and that is your duct leakage to the outside. So a basic picture of what's going on. I have moved my hose to be into the supply plenum because now I'm testing in an upflow furnace. So easier place is typically in the supply plenum. You can see the static pressure probe pointing into the airflow. I only have the hose attached to the input, not to the reference. So I'm bringing the manometer, the duct manometer to 0. And that is going to neutralize the leaks in the house. And I'm only going to get the leaks to the unconditioned spaces. If you're testing a duct system that's located primarily in one unconditioned zone, like this picture where the ducts are basically only in the attic, you have the option of setting up the gauge to measure building pressure with reference to that zone rather than with reference to outside. And the purpose of making this change is to ensure that the duct leaks located in that zone are subjected to the full test pressure. Since that's where the leaks are in the system, then those leaks could be pressurizing or depressurizing that unconditioned zone. And if that's the case, then we're not getting a test pressure of 25 across those ducts. So our test results are not actually in CFM 25. And so that's why you may want to actually have your reference hose going into that unconditioned zone. And that can be easier or harder depending upon the zone, figuring out how to get that hose up into that zone. You can do it from the outside. You can try doing it from the inside. You just have to figure that out. Here's the other setup. It'll yield the same results. It's adding a hose to the A side reference and putting that hose to the outside. And in that case, you are going to pressurize your duct system and the house to 25 pascals, neutralizing those inside leaks and only quantifying those leaks to the outside. The premise of duct leakage to the outside is that the duct leakage to the inside is somehow unimportant. The thought is that the conditioned air is still at least getting into the house, but that duct leakage that is being lost to unconditioned space is somehow more impactful. Well, duct leakage to the inside is a cause of comfort issues. It can also be a source of filter bypass, just like duct leakage to the outside. It can contribute to increased soil gas entry or other pollutants. It can cause CAS depressurization because it still can cause pressure differences across the duct system, therefore affecting the building enclosure. The one thing that it's not is that it's not a large energy penalty. So duct leakage to the inside can be just as important as duct leakage to the outside. Looking at the two tests, duct leakage, total duct leakage versus leakage to the outside. With total duct leakage, we only need the one piece of test equipment, the duct testing equipment. Duct leakage to the outside, we need the blower door and the duct testing equipment. So there's a shorter setup time for total duct leakage. We only need to set up the one piece of equipment. Total duct leakage can be performed at rough-in, whereas duct leakage to the outside, you have to wait until the building enclosure is finished. The duct leakage test is quicker once it's set up because you don't need to go back and forth between the two pieces of equipment. And then duct leakage is measuring all the leaks through the entire system. Duct leakage to the outside is missing the leaks to the inside. So now I'm not advocating that you choose one test over the other because one is easier to perform than the other test. That's not what I'm advocating. What I am advocating for is doing the test that provides me with the best information and to not waste my time with tests that don't enlighten me. In my building stock, my climate, what I find is shown in this slide. This is the same house, same attic system. I did total duct leakage and I did duct leakage to the outside. And this is what I have found over most houses in my building stock because the vast majority of ducts in my building stock are 100% outside the building enclosure, 99% outside the building enclosure. So my total duct leakage test gave me a reading of 259 CFM of duct leakage. My duct leakage to the outside test gave me a total of 250 CFM. Not enough difference or information for me to have spent the time to do duct leakage to the outside. So just want you, if you're not having to do a test for a particular standard or code or anything, you're actually trying to do your test for enlightenment of the homeowner, of you trying to find out what's going on in a home. Choose the tests that make sense and don't spend your time doing tests that don't make sense. All right, let's look at finding duct leaks. Finding duct leaks can be tricky, and it can also be really obvious, right? Finding a disconnected duct is incredibly obvious. Doing a good visual inspection of a duct system gives you plenty of visual clues. If you see dirty, impinged insulation, as in the picture on the right, then I know that there is duct leakage where that dirty insulation is. So you can often find your duct leaks through a good visual evaluation. Theatrical fog injected into a duct system is something that is taught and is often part of code rules in terms of finding accessible leaks or not. Personally, I've not found the use of fog to be particularly helpful in identifying duct leaks, especially if you're a one-person show and you need to set the whole thing up, get the smoke started, rush up, say, into the attic, and try to see where the leaks are. The smoke tends to very quickly overwhelm the space. If it's a system that's leaky enough that I'm putting smoke into it, the smoke has overwhelmed the space. It's hard to tell where exactly it's coming from. And it's typically coming mostly the air handler and the plenum, and just filling the attic with fog. The smoke also, it doesn't diffuse through that external vapor barrier on our insulated ducts. So the smoke can't tell me anything about inner flex linings, whether they're ripped or torn. But if you're going to do some fog testing, you want to use a theatrical fogger. The Energy Conservatory tells you that you should inject the fog stream toward the edge of the fan housing and not directly into the duct blaster fan motor. You want to clean off any theatrical fog residue from the fan motor and the fan housing. And you should definitely use a non-corrosive glycol water-based fog. Now, the newer Energy Conservatory fan, the Model 300, sorry, they say that they do not want any fog pulled through their fan. It will damage the motor. So what they suggest doing is to discharge the smoke into the flex duct, then attach the flex duct to the fan, and then turn the fan on. And once again, only use non-corrosive fog. Neither one of the fans is meant to be left on continuously for an extended period of time. The Energy Conservatory says specifically to not leave the fan on for more than 2 hours, and fogging a system looking for leaks should never take anywhere near it that long. Typical duct leakage locations are any joints, any seams, the boots, start collars, plenums, air handler, evaporator coil, cabinets, disconnections, rips, tears, holes, unducted platform returns. There's still old systems out there where the building cavities were used, so pan joists, poor connections between grills and boots and interior finishes, poorly fitting air handler doors and filter doors, and no P-trap in the condensate line, or the exhaust hole not placed in the proper place. If it's placed before the P-trap, then the condensate line continues to be an air leak. It needs to be placed after the P-trap in the condensate line for the condensate line to not be an air leak in your duct system. Total system airflow, right? Wrapping it up, we're on time. So to make sense of duct leakage, it helps to know how much air we are losing through those leaks. the blower fan in the air handler is creating the airflow. The amount of air that the blower fan is moving is the total system airflow. And duct leakage is the difference between what the blower fan is moving and what arrives in the house and what is drawn back into the system on the return side. Now, building code, at least in California, allows us to estimate nominal system airflow rather than having us measure airflow. And then building code gives us this maximum percentage of that nominal system airflow as allowable duct leakage for code compliance. So our allowable duct leakage percentage is basically based on a made up number. And studies show that system airflow in existing homes, unfortunately, is much, much lower than that nominal airflow that we're calculating and that code is allowing us to assume. And that translates into duct leakage actually being a higher percentage of capacity loss and therefore greater comfort issues and energy consequences for our systems. So what if we care more about performance and comfort than we care about code compliance? If that's the case, then we need to know actual performance and not assumed performance. This makes more data points and information important to us. We need to know what the appropriate airflow for the climate is, e.g., should we be getting dry climate airflow or should we be targeting humid climate airflow? What airflow range is the installed equipment capable of? How much air is the blower actually moving? How much energy is it taking to move that amount of air? How much of that air is actually making it into the conditioned space? Is the right amount of air making it into each room that has a supply grill? Can the delivered air be delivered at a velocity and throw that will mix the air to a comfortable temperature? Duct leakage and system airflow are parts of a much bigger picture that has to do with performance, energy efficiency, indoor air quality, and comfort. The best ways to measure total system airflow are the pressure matching method with the duct testing equipment, or the true flow grid, which is only manufactured by Energy Conservatory. The basic concept for measuring total system airflow is that, once again, we're measuring pressures and then we're performing a calculation to convert pressure to airflow in cubic feet per minute. So with the manometer and a static pressure probe inserted into one of three appropriate places in the system gets turned on and the normal system operating pressure is measured and documented. And so it's either stored in the manometer or you're writing it down. Then the device is installed into the system. And then the system is turned back on, but now the pressure has changed because there is now this device installed. We're bringing the pressure back to that normal system operating pressure that we measured. And the B side of the manometer is able to account for that pressure difference and do that calculation to tell us what the total system airflow is. So we begin with the air handler off. You open a door or window between the house and outside. You open the space where the air handler is to the outside or to the house, which is now connected to the outside. The supplies and returns are wide open. None of the system is taped off for this test. The filter remains in place to get the normal system operating pressure. A static pressure probe is inserted basically in the supply plenum, is one of the best places, pointing into the airstream. So now you're going to measure that normal system operating pressure. So you're connecting your tubing to the static pressure probe and the channel A input tap of the manometer, turning on the manometer to measure normal system operating pressure. You're pressing start, and you can see that the manometer is set to a pressure and air handler mode, and it's asking for the normal system operating pressure. So you press start, you wait for the number to stabilize, and then you press enter, and now the manometer can store that NSOP reading. Then you turn off the air handler, leaving the static pressure probe in place. To set up the equipment, you've already got your static pressure probe in place and the tubing set up between the manometer and that probe. You're next, if you're doing the pressure plenum matching, you're going to seal off the return opening in the air handler cabinet using tape and cardboard. So we're effectively sealing off the return side, and we are installing the duct test equipment at the blower compartment, and that now becomes basically the return side. It's where all the air can flow into the system from. So this way we're getting rid of any return side duct leaks in our reading, because we want total system airflow. You're going to connect tubing from your channel B input tap to the duct tester fan tap. And then you're going to choose your device, which should be either the air handler or the DBB, because you're already in pressure flow air handler. You're going to choose your device, which is DBB or True Flow. Or if you happen to be using the DBA, you would choose that. And you're going to configure the flow ring or flow plate on your config. So if airflow exiting from the duct blaster is severely obstructed by the air handler fan or any of the air handler components, then you may need to attach the blower compartment using that small cardboard box again to give more airflow. You're going to turn the air handler back on. Channel A will display the operating duct tester, this new operating duct pressure. You're going to turn the duct tester fan on, and you're going to adjust it to that normal system operating pressure. And that now is the total flow system operating pressure. And once you've got that within 5 pascals of that original reading, you should probably engage a time average and watch for your B side to stabilize. And once it stabilizes, you grab that number, and that is your total system airflow. And so that's basically the plenum pressure matching. The True Flow plate, when you take the measurement at the air handler, it provides a pretty simple, accurate measurement of total system airflow, and it's good for air handlers rated from 1 to 5 tons. If you have to use your plates at a central return, you're ending up catching return duct leaks. So that's not really your system airflow. So it has some limitations. It's adjustable, so it can be fitted into a bunch of different sized return openings, but it won't always fit. And so sometimes you end up having to do a bit of a paper mache project, or deciding that you can't use the True Flow plate in a system, and that's a limitation. And it cannot be used effectively if there's multiple returns in the system. You need to have True Flow plates at all those returns and be taking simultaneous readings, and that's not really feasible. And once again, you would be capturing duct leaks, return duct leaks. So here's the best location for total system airflow with the True Flow plate. It's at a filter slot right next to the air handler. And although Retrotech doesn't manufacture an equivalent piece of equipment, their manometers will work with the Energy Conservatory's True Flow plate. You don't close off the return side of the air handler. You remove the filter from the filter slot, and you install the True Flow plate in its place. And then there's these 2 tubes that are attached to the True Flow that you need to snake out of the return opening in some way without crimping them, and that can be a little bit tricky. And you may have to tape the filter door closed around those tubes But once the plate's in and those tubes are out, you hook them up to the manometer, you turn the system back on, put it on a time average, and it's adjusting for that pressure difference between the programmed in normal system operating pressure, and will give you the flow reading on channel B of your total system airflow. So that's total system airflow. And now we have all kinds of real data points to work with to improve the system performance, or to decide if maybe we need to recommend that a new system be installed instead. So in summary, the airflow rate through residential air handlers is an important variable for optimizing the performance of forced air heating and cooling systems. Reduced flow rate is one of the prime reasons that HVAC systems underperform. Air leakage in forced air duct systems is a major source of energy waste in both new and existing homes. Duct leakage degrades indoor air quality and can cause combustion safety issues. And in my opinion, controlling duct leakage to the inside is just as important as controlling duct leakage to the outside. So I hope that I have broadened your understanding of duct leakage testing, and its importance in the bigger picture of HVAC system performance today. My contact information is info@judyrachel.com, and we've got a couple minutes at least for any additional questions. And Sean, are you there? Anybody out there?
I'm here. Yeah. I do see one raised hand from Timothy. Timothy, feel free to hop in with your question. And
yeah, I see that, you know, your main focus is the duct testing, but I'm finding a lot of people that do blower door tests do duct testing also in conjunction with the blower door test. Is it as accurate using those methods?
So if you are asking about using like the blower door subtraction method to determine what duct leakage is, so not attaching duct test equipment and using something like that blower door subtraction method, it's not anywhere near as accurate. Yeah. And so we really need to use the duct test equipment if we want to have apples to apples comparisons about what's going on with the duct system, or to come up with, you know, some kind of accurate estimate. Because once again, even with the duct test equipment, it's an estimation of the duct leakage because we can't really test at normal operating pressures. We're using that 25 pascals as a proxy.
Mm-hmm. Yeah, it looks like your method is much more accurate and targeted than someone that doesn't have that type of equipment that you have to really see what's going on with the duct system.
Yes. Thank you, Timothy.
And Javier, I also saw your hand up earlier. Did you have a question?
Hi, Judy. Just had a question now. How often you calibrate your equipment? But what's the best way?
Yeah, so as you can see, I ran out of time, and so it's kind of a good thing, unfortunately, that I didn't put that in the presentation because that is important. The manometers, so it depends on the manometer that you own, and the manufacturer gives you the best information as to when you should send your manometers in for calibration. The DG700s, I think that they want them back every 2 years, and they're basically phasing those out. So they are actually giving you a discount on buying a DG1000 if you send your DG700 back to them, but they will still support those for a number of years yet. But I think that it's like 2 years for the DG700s, and since the DG1000s are still new, they started out at 2 years, but they recently came out with a bulletin that is showing that it's either 3 or 4 years that they're asking you to send those back for calibration. And RetroTech, I'm not 100% sure what their guidance is. It's probably within those same ballparks in terms of the calibration of their manometers. You also need to make sure that your fan sensor doesn't get damaged or bent in any way. So you should pretty much always be taking a look after every job, especially if you've dropped your equipment, to make sure that the flow sensor hasn't moved. And there are these kind of in-field proxy calibration ring methods that you hook your manometer up to your flex duct and your fan and take it to a test pressure and make sure that your manometer is reading that test pressure to give you a sense that your duct equipment or your blower door equipment, but your duct equipment is still calibrated properly. And that, you know, kind of depending on how hard you are in your equipment and how often you take it out in the field, you know, possibly once a month, once every 6 months, you should be checking that calibration. Great question, Javier.
So to follow up, I have the DG700 and it's a bit old. Have you tried the DG1000 and what do you think if you have?
I love my DG700s. It's why I use them in this presentation. They are visually so, they kind of just lead you through and tell you what you need to do your tests. So I hate the taps on the DG1000, having the, you know, them right in a row and so close together. You know, they're at least marked once the digital display comes up, so I know which is input and which is reference, and it does at least go from left to right, you know, just kind of like our DG700s. They take a long time to boot up. The DG1000s, you know, it's, I don't know, you know.
I'm happy with mine, so I think I'll just wait.
Yeah.
Thank you.
Yeah. Anybody else? I'm seeing 2 things in the chat. All right, thank you. Thank you. Thank you all for attending. We're kind of just over the time. So Sean, I'm thinking that if there aren't more questions, I want to thank 3C Ren and everybody for attending today. And I think that we can all go on with our days. So thank you.
Yeah, and Judy, thank you for being with us today. Really appreciate it and sharing your wealth of knowledge. Yeah, I think we're at time, and I think we'll end here. But thank you so much, and thanks everyone for joining as well. Have a great day.
Absolutely, thank you.